Welcome back. This is Physics 104A, Chapter 7 homework. Chapter 7 is on conservation of energy. We'll start with number 12. Find the potential energy associated with a 70 kilogram hiker, A, atop New Hampshire's Mount Washington, 1,900 meters above sea level, and B, in Death Valley, California, 86 meters below sea level. Take the zero of potential energy at sea level. All right, so the y that we're looking for, the height, is going to be how much it is above the zero, which is above sea level. So for part A, we have the mass times g times the height of 1,900 meters, and we multiply those and we get 1.3 megajoules. For part B, we're looking at a height of negative 86 meters, so this will give negative potential energy. So 70 kilograms times 9.8 newtons per kilogram times negative 86 meters is negative 59 kilojoules. Number 15. How far would you have to stretch a spring with K equals 1.4 kilonewtons per meter for it to store 210 joules of energy? Here is the equation that the potential energy stored in a spring is 1/2 kx squared. We're going to algebraically solve that for x. So we get x is the square root of 2 times the potential energy divided by k. And we plug in the values. That 1.4 kilonewtons per meter is 1,400 newtons per meter, and we get 0.55 meters. Number 16. A biophysicist grabs the ends of a DNA strand with optical tweezers and stretches it 26 micrometers. How much energy is stored in the stretch molecule if its spring constant is 0.046 piconewtons per micrometer? So it's the same formula we used in number 15. The only thing is we need to be very careful about the units. These are not MKS units. I'll start by writing out the given information, 26 micrometers and 0.046 piconewtons per micrometer. We use the equation potential energy is 1/2 kx squared. And notice that both the distances for x and also in the units for k are in micrometers. So if we leave those as they are, you see what happens to the units. Well, we multiply the numbers and they get 15.5, but look at what happens to the units. Piconewtons per micrometer times micrometer squared, that gives us piconewtons per micrometer. Now we want to get this in joules. It's asking how much energy. So an easy way to convert that is just to turn piconewtons into 10 to the negative 12 newtons and turn micrometers into 10 to the negative 6 meters. And so now we have 15.5 times 10 to the negative 12 times 10 to the negative 6, and that'll be in Newton meters, which is joules. So we get 1.55 times 10 to the negative 17 joules. Now, we could also do that problem, you can see in the green ink my solution, by starting out doing it in MKS units. So that would mean converting K, converting from piconewtons to newtons, and from micrometers to meters. You can see the conversion that I've done, and it's 4.6 times 10 to the negative 8 newtons per meter. And then when we plug it into the equation, U equals 1/2 kx, well, we just found K in newtons per meter. X being 26 micrometers is 26 times 10 to the negative 6 meters. Be sure to square it. And again, you get 1.55 times 10 to the negative 17 joules. Number 18. A 10,000 kilogram Navy jet lands on an aircraft carrier and snags a cable to slow it down. The cable is attached to a spring with K equals 40 kilonewtons per meter. If the spring stretches 25 meters to stop the plane, what was its landing speed? All right, let's set this up as a conservation of energy problem, and we think about the two different states. State 1 is the speed that the plane is going when it lands. It's going at a very fast speed. State 2 is when it has been brought to rest. Now, we don't have to invoke any other energies. There's no gravitational potential energy to consider because at the point that it lands and the point where it's brought to rest, those are the same height. During state 1, the spring is at equilibrium, so that's 0. During state 2, of course, it's brought to rest, so there's no kinetic energy. So this is it right here, just these two terms. All of the kinetic energy becomes all the potential energy stored in the spring. So we take this equation, we're going to solve for V, and we get, using the algebra, V equals square root of kx squared over m. If you want to, you can bring the x squared outside of the square root, making it just x. And then we have 25 meters times the square root of 40,000 newtons per meter divided by 10,000 kilograms, and we get 50 meters per second. Number 20. In a railroad yard, a 35,000 kilogram boxcar moving at 7.5 meters per second is stopped by a spring-loaded bumper mounted at the end of the level track. If K equals 2.8 meganewtons per meter, how far does the spring compress in stopping the boxcar? And I hope you can see that when we set up the energies, it's actually the same as number 18 above. We have all the kinetic energy equals all the potential energy in the spring when it's brought to rest. However, here we're solving for x. So doing the algebra, x is v times the square root of m over k. We're going to plug in those values, and we get 0.84 meters. Number 21. You work for a toy company and you're designing a spring-launched model rocket. The launching apparatus has room for a spring that can be compressed 14 centimeters, and the rocket's mass is 65 grams. If the rocket is to reach an altitude of 35 meters, what should you specify for the spring constant? Okay, so we have x is 0.14 meters, the mass is 0.065 kilograms. I'm putting all these in MKS units. We want y, the height, to be 35 meters, and what is k? We'll set the two states as E1 at the launch, meaning when the spring is fully compressed, and E2, this is when it's at its maximum height, and so that's going to be mg times y. And once we set that up, we solve for k, 2mgy over x squared, plug in the values, and we get 2,300 newtons per meter. Number 24. A particle slides along the frictionless track shown in figure 716, so that's given in the book on page 130, starting at rest from point A. Find part A, its speed at B, and part B, its speed at C, and part C, the approximate location of its right-hand turning point. All right, so taking from the picture that's given in the book, we need the height at A is 3.8 meters, the height at B is 2.6 meters, the height at C is 1.3 meters. Part A is asking the speed at B. So we'll set up these two states, the state when the car is at A and the state when the car is at B. And so when it's at A, it says it's at rest. And so the only energy is its gravitational potential energy, so mgya. When it's at B, it's got the potential energy, mgyb, plus it's got kinetic energy, 1/2 mvb squared. And we want to solve for v sub b. And the first thing I see to do is to divide the entire equation by m. And what we get when we solve for v sub b is we get a plus or minus square root of 2g times ya minus 1b. That plus or minus just means that it could be going in either direction. When we plug in the values, we get that it's going at a speed of 4.85 meters per second. Now, the velocity is plus or minus 4.85 meters per second. The question did ask the speed, which is going to be the magnitude, so it would be good to just say 4.85 meters per second. Now for part B, it asks for the speed when it's at C. We don't have to go through all the work again. We've already done the work for part B. It's the same thing. All we're going to do is switch out our letters B for C, and we get that the speed of C is plus or minus square root of 2g times the difference in height of YA minus YC. Looking in the picture, C is lower than B was, so we expect it's going to be going faster than it was at B, and there it is, 7 meters per second. And part C asks its approximate location of its right-hand turning point. And in the picture given, there's a number line. And so it will turn when it reaches the same height as A. And if you look in the picture, this is approximately at 11 meters. Number 25. A particle slides back and forth on a frictionless track whose height as a function of horizontal position x is y equals ax squared, where a is 0.92 per meter. If the particle's maximum speed is 8.5 meters per second, find its turning point. All right, let's draw a picture here. We can draw this picture, y equals 0.92 x squared, and without any scale, any horizontal or vertical tick marks, we can just draw it simply as a parabola that is centered at x equals 0. We have that at x equals 0, max speed is 8.5 meters per second. Now we should know, it doesn't explicitly tell us the max speed is down there, but we should intuitively know that because that's where it's at its lowest point. That's where it's at its lowest potential energy, so it will be going the fastest down there. And it will be going at 0 at the turning point at its maximum height, and also there's another turning point to the left. So I've set these up as state 1 at the bottom and state 2 at the top of its trajectory. Conservation of energy, E1 equals E2. And we'll think about the different energies. At E1, it's at a height of 0. I'm sorry, at state 1, it's at a height of 0. So it's got kinetic energy, 1/2 mv1 squared. At state 2, it's got no kinetic energy. It's got all potential energy, so mgy2. And we are to find out where that y2 is. So we're going to take that equation, solve it for y2, v1 squared over 2g, plug in those values, and we get a height of 3.686 meters. That's where its turning point is. The question asked, find its turning points. And we really should find this the x value of those turning points. So we have the y value, but let's find the x value. Well, let's go back to the equation, y equals 0.92x squared. And we know what y is, so now solve for x. Remember, there is a plus or minus when you take the square root of both sides. And so we plug that in, and we get plus or minus 2 meters. So it'll be plus 2 meters with a height of 3.686. and minus 2 meters with a height of 3.686. Number 26. A particle is trapped in a potential well described by U equals 16x squared minus B, and B is 4 joules. Find the force on the particle when it's at 2.1 meters, 0, and negative 1.4 meters. All right, so here is the potential energy function. It's given in MKS units, so meters and joules. Force is the negative derivative of that. So we'll take the derivative, put a negative sign on it, and it becomes negative 32x. And now we just plug in the various values for x. So at x equals 2.1, and on the diagram down below, that might be around right here-ish. And we get the force is negative 67 newtons. And we want to look at the picture and see if that makes sense. Negative and pretty big force relative to the other answers that we get. So that means it's steep, and negative means it's going to get pulled, it's going to go to the left. And that looks right. Part B, when x equals 0, we plug it in, we get force is 0. 0 newtons, and we think right here, yeah, that's going to be 0 force. It's just going to sit there at the bottom if we were to place it there. And for x equals negative 1.4 meters, maybe that's about right here, and we plug in the negative 1.4 and we get 45 newtons. And then we assess by the picture, yeah, it's positive because it's going to be pulled to the right. Number 31. In figure 7.7, take the spring to have K equals 87.5 newtons per meter and consider the track to be frictionless. A 50.2 gram mass is initially pushed against the spring, compressing it 7.88 centimeters. When the mass is released, to what vertical height up the track does it rise? All right, so figure 7.7, you can see that in the book in example 7.5. And we're going to take the two energy states, I've called them 0 and 1, and the 0 state is when it's compressed against the spring, it's all potential energy, 1/2 kx squared, and then it goes up to some height. So at state 1, it's at that maximum height, so it's at a height of mg times, you could say h or y. I follow what the example in the book did, I called it h, and that's the potential energy. And then we're going to solve for height. This actually follows exactly like the example in the book. Example 7.5, and so you plug in those values and you get a maximum height of 0.552 meters. Number 40. As a highway engineer, you're asked to design a runaway truck lane on a mountain road. The lane will head uphill at 30 degrees and should be able to accommodate a 16,000 kilogram truck with failed brakes entering the lane at 110 kilometers per hour. How long should you make the lane? Neglect friction. All right, so let's draw a picture here. You can see the slope 30 degrees. Relevant to conservation of energy is the height it's going to go. And we want to know how long should the lane be. So that's going to be the hypotenuse of our triangle. Since it's nicely, conveniently a 30-degree angle, we know that for a 30, 60, 90 triangle, the hypotenuse is twice the short leg, so it's just going to be twice the height. Although if it were anything other than 30 degrees, we would want to do the trigonometry to figure out what that hypotenuse is. But ultimately, it's that length we're going to solve for. And here in the red block, I've done the trigonometry to show you sine of 30 degrees is h over L, and you can follow it and get L is 2h. All right, so energy at state 0 when the truck enters the runaway truck ramp and it's going full speed, and then when it gets to its maximum height with 0 speed. So down at the bottom, which I'm going to call the height of 0, so potential energy is 0, it's 1/2 mv0 squared. Up at the top, it's all potential energy because it's come to rest and it's mgh. We're going to solve for height. So height is, do the algebra, you get v0 squared over 2g. You need to convert the speed. It says 110 kilometers per hour, so we need to convert that to meters per second. That's 30.5 repeating meters per second. Plug that in, you get a height of 47.635 meters. From the trigonometry with the 30-degree angle, we then get the length of the ramp needs to be 95 meters. And that is neglecting friction. The reality is there would probably be some friction, and so the truck wouldn't go that far. Number 42. A child is on a swing whose 3.2 meter long chains make a maximum angle of 50 degrees with the vertical. What is the child's maximum speed? All right, let's draw a picture here. We have when the swing is hanging vertically, there's the length L, and when it's at some angle theta, the L has swung out this way. And so let's think about two different states. State 0, when the swing is at the bottom, height is 0, because I've called y0 0. When it's at this maximum height with the 50-degree angle here at y1, we have to do a little bit of trigonometry to figure out what is the height of y1. So look at my picture here. We have the full length, and let's call the short leg of the triangle B. And therefore the height at 1 is going to be whatever L minus B is. So let's look at that right triangle. We can say the cosine of theta is adjacent over hypotenuse, so it's B over L, which means B is L cosine theta. We know that y1 is this full length L minus B. So let's say y1 is L minus, and we'll substitute in L cosine theta. Let's clean that up a bit by factoring out L. So the height of y1 is L times 1 minus cosine theta. Now that we know those dimensions, now let's apply conservation of energy. E naught equals E1. So at state 0 at the bottom, it's all kinetic energy, 1/2 mv naught squared. At the top of the swing, it's potential energy, mgy1. We're going to divide out the mass, and we get V naught is square root of 2gy1, and now we're going to do what I did at the top of the page, substituting in for y1, L times 1 minus cosine theta. So there it is, and now we can plug in all the values, and we get a maximum speed of 4.7 meters per second. Number 45. There's a diagram in the book. I've reproduced it more or less on the top of the page. A 200-gram block slides back and forth on a frictionless surface between two springs, as shown in the picture. The left-hand spring has K equals 130 newtons per meter, and its maximum compression is 16 centimeters. The right-hand spring has K equals 280 newtons per meter. Find the maximum compression of the right-hand spring and the speed of the block as it moves between the springs. All right, I've listed out the given information. Because the right-hand spring has a greater spring constant, it's going to compress less than the left-hand spring. So if the left-hand spring was 16 centimeters, we know it's going to compress less than that. Notice also I've done it all in MKS units, so x1 is 0.16 meters. And let's set up conservation of energy. I'll call state 1 when the left-hand spring is compressed, state 2 when the right-hand spring is compressed, and later on we'll get to state 3 when it's in the middle. So we'll set up E1 equals E2. In both of those states, it is one spring that is fully compressed. So 1/2 K1x1 squared equals 1/2 K2x2 squared. We do the algebra solving for x2, and it becomes this ratio that x2 is x1 times the square root of k1 over k2. So we can plug in those values, and we get 10.9 centimeters, which rounds to 11 centimeters for two significant figures. Then in part B, we need to compare the energy at state 3. Now we can do it either with state 1 or state 2. I'm going to prefer to do it with state 1 because state 2, the information I know about it, the spring compression, is something I solved for. And I'd be more confident in going from the given information, not something that I solved for because I could have made a rounding error, I could have made a mistake somewhere. And so it's just safer to go with the given information. So E3 equals E1. 1/2 mv3 squared equals 1/2 k1x1 squared, because in state 3 it's all kinetic energy. Both of the springs are at equilibrium. Notice that mass will not divide out because it's only a factor on the left-hand side. So we get V3 is plus or minus the square root of K1 over M. That plus or minus refers to that the velocity could be going to the left or to the right, although the question does simply ask for speed, which is going to be the magnitude of that. When you plug in the values, you get plus or minus 4.1 meters per second, and the speed, therefore, is 4.1 meters per second. We can check our results by computing energy at each point. It should be constant. So the energy at 1 is 1/2 K1x1 squared from the given information, 1.66 joules. The energy at 2, 1/2 K2x2 squared. So we're going to plug in what I believe x2 to be based on my solution. And don't use 11 centimeters, the rounded off version. Take it out a few more digits so you don't get a rounding error. And that comes out to be 1.66 joules. So that gives me good confidence that I did part A correctly. And for part 3, in state 3, all of its energy is kinetic energy. So I'm going to plug in 1/2 mass times what I believe the speed to be, 4.079 meters per second. Square that, and we get 1.66 joules. So it comes out in all 3 cases as the same energy. Number 50, a particle with total energy 3.5 joules is trapped in a potential well, given by the potential energy function there. U is in joules, X is in meters. Find its turning points. Having a picture to look at sure is nice. Looks kind of like a roller coaster. It goes down and up. The total energy is this line at 3.5 joules. And so the picture helps us to see and to recognize what we're dealing with, that the turning points are where kinetic energy is 0. And that's where, as I've written here to the left, energy is equal to potential energy plus kinetic, which is 0. So energy is equal to potential energy. So this is what we're going to do with the equation. Energy equals potential energy. So 3.5 joules equals 7.0 minus 8.0x plus 1.7 x squared. Then we're just going to solve for x. So I'll put that in standard form. We have a quadratic equation here. You can solve it either by graphing or by the quadratic formula. And so however you solve it, you get x of 0.488 meters, which is on the left, and 4.22 meters, which is on the right. Number 52. In ionic solids such as sodium chloride, the potential energy of a pair of ions takes the form of U equals B over R to the N minus A over R, where R is the separation of the ion. For sodium chloride, A and B have the SI values of 4.04 times 10 to the negative 28 and 5.52 times 10 to the negative 98 respectively, and N is 8.22. Find the equilibrium separation in sodium chloride. And it says in the book SI values, international system, more specifically, those are the MKS values, so meters, kilograms, and seconds. All right, now we look for what does it ask for? Find the equilibrium separation. So we want to solve for R when it's at equilibrium. So that means where potential energy is minimized. To find where potential energy is minimized, we're going to take its derivative and set it equal to 0. So taking the derivative, nice little calculus exercise here, is looking up at the equation at the top, negative n br to the negative n minus 1 plus ar to the negative 2. Now just be careful with the calculus. Where did that plus sign come from? Well, it came from when we dealt with this negative 1 exponent, it became the coefficient, so it became minus negative 1, which is plus, and then the exponent went down by 1. So there it is, equals 0. And depending on your comfort level, at any time you can plug in the numbers, and I left N and B and A out, actually one of the N's out, but I just wanted to plug in N up here in the exponents because it helped me better to see what exactly am I doing as I do the factoring. So what can we factor out? Well, of these two terms in the left-hand side, you can factor out the lowest exponent of R. And again, I plugged in the n values in those exponents because it helps me to see what is the lowest exponent of R. And so R to the negative 9.22 and R to the negative 2, I'm going to factor out that R to the negative 9.22. And when I factor it out of the first term, it just completely goes away. It becomes 1 actually. And the second term, I'm going to take that negative 2 and subtract negative 9.22, and it becomes 7.22. So this is what it looks like after factoring. Make sure that you understand how that factoring works. And now we have, in the line where my red pointer is at, we have two factors. multiplied to give 0. And that means that one of them must be equal to 0 for a true solution. And the first one can't be 0 because it's something to the negative power. And something to a negative power cannot be 0. So we can just rule that out, which means if there is a real solution, it must be this bit in parentheses. So I'm going to set this equal to 0 and solve for r. So I get AR to the 7.22 equals NB. I'm going to divide both sides by A and put it to the 7.22th root, or put it to the power of 1 over 7.22. And so finally, I plug in all those values. I get 2.82 times 10 to the negative 10 meters, or often when talking about molecular distance levels, we use angstroms. So an angstrom is 10 to the negative 10 meters, so we can say 2.82 angstroms. Number 61. A child sleds down a frictionless hill whose vertical drop is 7.2 meters. At the bottom is a level but rough stretch where the coefficient of kinetic friction is 0.51. How far does she slide across the level stretch? All right, so I hope we haven't forgotten how to deal with our force of friction. I've drawn a picture here. I'm going to call her initial height at state 0, 7.2 meters. Final height, y1, is 0 meters. And so there's state 0, state 1, and conservation of energy applies between 0 and 1. But then once we hit the bottom, it says enters a rough stretch where there's friction. So once we hit the bottom, we have to understand conservation of energy will no longer apply. And so we can't use conservation of energy going from state 1 to state 2. And so here's the strategy. I'm going to use the work energy principle, which is that change in kinetic energy is work done. The kinetic energy going from 0 to 1 is going to be taken away by friction, going from 1 to 2. And so going from 0 to 1, we set up conservation of energy, and we can say mgy0, the total energy at state 0, is kinetic energy at state 1. Now, I'm bypassing the need to figure out what her speed is. So you notice I'm not putting for state 1 1/2 mv1 squared. And we could do that, but that's actually an unnecessary step. But you're welcome to try it. It's another way of solving it. I'm just going to leave that as kinetic energy at state 1. All right, going from 1 to 2, the work energy principle is that her change in kinetic energy is equal to the work done by friction. So change in kinetic energy, well, final kinetic energy is 0, initial kinetic energy is K1, and now you can see that's why I left it as K1 there. So 0 minus K1 equals work done by a force in one dimension, or a constant force rather, is going to be the force, so that's the force of friction, times displacement, times the cosine of the angle between them. You see my little green picture here, there's a 180-degree angle. Friction always goes 180-degree angle to displacement. And so let's clean this up. We now have on the left-hand side negative kinetic energy 1 equals, remember force of friction is mu sub k normal, so negative mu sub k normal times displacement. The negative sign came from the cosine 180 degrees. Clean this up some more. Normal force on a horizontal surface is mg. And look at this, we have mg on the right, mg on the left. Let's divide those out. And we're left with y0 equals mu sub k delta x. And let's finally solve for delta x. y0 over mu sub k, 7.2 meters over 0.51, so we get 14 meters. Now, another solution we could have done using F equals ma and kinematics. So on the last page, I said I'm not gonna do this. I just left the state of E1 as kinetic energy, but I said there is another way. So let's look at it this way. Conservation of energy shows the speed at y1. So again, comparing state 0 and state 1, mg y0 equals 1/2 mv1 squared. We solve for v1 and get that speed. Now, let's consider the path going from 1 to 2. And I have my force diagram here. F equals ma in the x direction. Negative friction equals ma. And friction becomes mu sub k mg. So negative mu sub k mg equals ma. Let's divide out m. We're going to use kinematics to solve for delta x. And ultimately, that's what we need to solve for, delta x on that friction surface. So v2 squared equals v1 squared plus 2a delta x. Solve that for delta x. v2 is where she's come to rest, so that goes to 0. We have v1 squared, negative v1 squared over 2a. And so now let's plug in things that we found. What is v1 squared? Well, go up to the top here, and v1 is square root of 2gy0. So v1 squared is 2gy0. There it is in the numerator. 2 times acceleration. What is acceleration? Well, let's go up to this line. Negative mu sub kg. And so we have this right here. And then things divide out. The 2's divide out, the g's divide out, the negatives divide out, and we're left with delta x equals y0 over mu k, which is the same solution, the same thing we got from my first solution that didn't even involve finding the intermediate velocity. So we get 14 meters. And that is the end of the Chapter 7 homework. Have a great day.